Welcome to the thermal crucible. This video explores how engineering overcame the extreme heat in jet engines using fluid dynamics, metallurgy, and atomic design. The jet engine presents a fundamental paradox. Modern turbine blades operate in gas streams significantly hotter than their own melting point. How do they survive 20,000 gigaseconds of spinning force? The turbine's job is to extract energy from the heated flow to drive the compressor. This involves thermodynamic calculations to determine the total work extracted and the turbine pressure ratio. Surviving the thermal crucible requires a synergistic defense system. We will explore this blade layer by layer, from fluid dynamics down to the atomic lattice. Layer 1 is the external deflector. Cooler air is bled from the compressor and forced out through microscopic holes. This creates a high-pressure coolant film that blankets the metal, pushing the 1627 degrees Celsius gas away. Heat removal uses architectures like convection through internal routing, impingement with high-velocity jets, film cooling with angled air exits, and effusion via a porous surface structure. Layer 2 is thermal armor, a ceramic thermal barrier coating, typically yttria-stabilized zirconia. Its extremely low thermal conductivity acts as a shear cliff, reducing the surface temperature by up to 200 degrees Celsius before the heat reaches the metal. This synergistic approach solves the paradox. Through stacked defense, the 1627-degree external gas never actually touches the superalloy. By the time the energy reaches the metal, it is safely below the 1400-degree melting point. The complex internal cooling channels are created using investment casting. A sacrificial ceramic core is 3D printed, surrounded by wax and a ceramic shell. The wax is then melted out, and molten superalloy is poured in. Layer 3 is the superalloy matrix. Nickel-based superalloys get strength from a two-phase structure, the gamma-phase mortar, and the rigid, cuboidal gamma-prime bricks, which block atomic dislocations and retain structural strength at 1100 degrees Celsius. Material scientists are engaged in a chemical arms race, constantly tweaking alloy compositions. Adding rhenium slows dislocation movement, improving creep resistance. Adding ruthenium stabilizes the microstructure, pushing temperature limits past 1120 degrees Celsius. Layer 4 addresses the enemy within creep. Under extreme force and heat, the atomic structure stretches and tears. The weakest links are the grain boundaries, which are chaotic fault lines. To survive, these must be eliminated. The evolution of the crystal structure eliminated these fault lines. Early equiaxed polycrystal blades had high creep susceptibility. Directionally solidified blades eliminated transverse boundaries. Modern turbofans use single crystal blades with zero grain boundaries for ultimate thermal fatigue strength. The single crystal blade is created using the pigtail selector. By solidifying the molten superalloy through a smooth, bent helix, the mold admits only one crystal orientation. This single crystal grows to form the entire blade, leaving no boundaries. The modern turbine blade is the pinnacle of engineered survival, a masterpiece of integrated science. It uses fluid dynamics to deflect heat, chemical coatings to insulate, and a flawless atomic lattice to hold it together, operating in a crucible hotter than its own melting point.